So here's something worth thinking about as you settle in tonight. You've spent roughly a third of your life asleep. If you're, say, 30 years old, that's about 10 full years of unconsciousness. 10 years. And during a huge portion of that time, your brain has been doing something that, honestly, science still doesn't fully understand. It's been dreaming, building entire worlds from scratch, populating them with people you know and people you've never met, running you through scenarios that range from the mundane, like being late for a meeting you forgot about, to the absolutely surreal, like flying over a city made of glass, while your childhood dog explains quantum physics to you. And the strangest part isn't that your brain does this. The strangest part is that while it's happening, you almost never realize it isn't real. That's worth sitting with for a second. Your brain, the same organ that lets you do calculus, that lets you recognize a friend's face in a crowd of thousands, that keeps your heart beating and your lungs breathing without you ever having to think about it. That same brain, every single night, constructs an elaborate hallucination and then falls for its own trick. You experience it as completely real. You feel the fear, the joy, the confusion, the embarrassment. Your heart rate changes. Your breathing shifts. Sometimes you cry. Sometimes you laugh. And then you wake up. And within minutes, most of it dissolves like fog. So tonight, let's talk about all of it. Let's talk about what dreams actually are. Not in some hand-wavy poetic sense, but mechanically, neurologically. What is happening inside your skull when you dream? Let's talk about why we dream, which turns out to be one of the most fiercely debated questions in all of neuroscience. Let's talk about the weird stuff. Why you can't read in dreams. Why your teeth fall out. Why you sometimes realize you're dreaming and suddenly have control over everything. And let's start where any good story starts, which is at the very beginning, with the people who first tried to make sense of this bizarre nightly phenomenon thousands of years before anyone had the faintest idea what a neuron was. Because humans have been obsessed with dreams for as long as we've been human, and I mean obsessed. Some of the oldest written texts we've ever found are about dreams. There's a Sumerian tablet from around 3100 BCE, so we're talking 5,000 years ago, that describes a king's dream and what it was supposed to mean. The ancient Mesopotamians had professional dream interpreters. This was a real job. You'd have a particularly vivid or troubling dream, and you'd go consult someone whose entire career was built around telling you what it meant. They believed dreams were messages, communications from gods or spirits or the dead, slipping through into your sleeping mind. And honestly, you can understand why they thought that. Think about what a dream feels like from the inside when you don't have any framework for understanding brains or neurons or REM sleep. You close your eyes, you lose consciousness, and then suddenly you're somewhere else, seeing things, hearing things, interacting with beings that seem to have their own will and their own agenda. If you didn't know about neuroscience, if you had no concept of the brain generating its own internal experience, what else would you conclude? Something from outside must be putting those images there. It's actually a perfectly rational inference given the information available. The Egyptians took this even further. They had a whole text called the Chester Beatty Papyrus. It dates to around 1275 BCE, during the reign of Ramesses II, and it's essentially a dream dictionary. It lists different dream scenarios and what they supposedly predict. If you dream of drinking warm beer, that means suffering is coming. If you dream of seeing a large cat, that means a large harvest is on the way. They categorized dreams as either good or bad, and the interpretations were taken seriously at the highest levels of society. Pharaohs made military and political decisions based on what they dreamed. This wasn't superstition pushed to the margins. It was woven into the fabric of governance. The Greeks, though. The Greeks are where things start to get really interesting, because the Greeks were the first culture we know of where someone stood up and said, actually, maybe dreams aren't messages from the gods. Maybe they come from inside us. That someone was Aristotle. Around 350 BCE, he wrote a short treatise called On Dreams, in Greek, Perianipnion, and in it, he made an argument that was genuinely radical for his time. He said dreams are not divine. They're a natural phenomenon. His reasoning was elegant in its simplicity. He pointed out that animals dream too. Dogs twitch and whimper in their sleep. Horses' legs move as if they're running. And if dreams were messages from the gods, why would the gods bother sending messages to animals? It doesn't make sense. Therefore, dreams must arise from some natural process within the dreamer. Now, Aristotle didn't get the mechanism right. He thought dreams were caused by residual sense impressions, like after images left over from waking experience that your mind replays and distorts during sleep. But the core insight, that dreams are generated internally by the dreamer's own mind rather than received from some external source, that was a genuinely profound leap. And it took roughly 2,000 years for Western thought to fully catch up to it. Because after Aristotle, the divine interpretation of dreams came roaring back. Early Christianity embraced the idea that God spoke through dreams. The Bible is full of prophetic dreams. Joseph interpreting Pharaoh's dreams of fat cows and thin cows. Jacob's ladder, the angel appearing to Joseph in a dream to tell him about Mary's pregnancy. Throughout the medieval period, the dominant view in Europe was that dreams were either divine messages or demonic temptations, and trying to analyze them through natural philosophy was, at best, a waste of time, and at worst, borderline heretical. So for centuries, dreams remained in the domain of theology and folklore rather than anything we'd recognize as science. And then, in the late 1800s, everything changed. And the person who changed it was, of course, a Viennese neurologist with a very famous beard. Sigmund Freud published The Interpretation of Dreams, Die Traumdeutung, in November of 1899, though the publisher actually printed the date as 1900, maybe because it seemed more fitting for a new century. And here's the thing about Freud. Modern neuroscience has moved well beyond most of his specific theories, and some of his ideas have been pretty thoroughly debunked. But it's hard to overstate how important this book was, not because Freud was right about everything, but because he did something no one had really done before at that scale. He took dreams seriously as a subject of systematic investigation. He treated them as data. He said, look, these aren't random noise and they aren't messages from God. They're meaningful products of the mind, and if we study them carefully, they can tell us something real about how the mind works. Freud's central claim was that dreams are, as he put it, the royal road to the unconscious. He believed that every dream, no matter how bizarre or nonsensical it seems on the surface, is actually the disguised fulfillment of a repressed wish. The idea was that you have desires, often sexual, often aggressive, often socially unacceptable, that your conscious mind can't or won't acknowledge. During sleep, when your conscious defenses are lowered, these wishes try to express themselves. But even in sleep, there's a kind of internal censor, Freud called it the dream work, that disguises the true wish, wrapping it in symbols and metaphors and narrative displacements so that it becomes unrecognizable. The dream you actually experience and remember, the surface-level story, Freud called the manifest content. The hidden wish underneath, the thing the dream is really about, he called the latent content. And the job of psychoanalysis was to work backward from the manifest to the latent, to decode the dream and reveal the buried desire. It's a beautiful theory in a way. It's elegant, it's dramatic, and it gives every dream a hidden meaning, which is deeply satisfying to the human desire for narrative and significance. The problem is that it's very hard to test scientifically. How do you prove that a dream about, say, climbing a staircase is really about something else entirely? Freud's method relied heavily on free association. You'd describe your dream to an analyst, and then say whatever came to mind about each element, and the analyst would interpret the connections. But different analysts could reach very different interpretations of the same dream, and there was no objective way to determine which one was correct. The theory was, in a sense, unfalsifiable. It could explain anything, which means it really explained nothing in a rigorous scientific sense. But Freud's lasting contribution wasn't his specific theory of wish fulfillment. It was the idea that dreams are worth studying scientifically at all. He opened the door, and once that door was open, other people walked through it with very different tools. And the most important of those people, the ones who truly cracked open the science of dreaming, were two researchers working at the University of Chicago in the early 1950s. Their names were Eugene Oserinsky and Nathaniel Kleitman, and what they discovered was, genuinely, one of the most important findings in the history of sleep research. Maybe the most important. Oserinsky was a graduate student, and Kleitman was his advisor, a physiologist who'd been studying sleep for decades, and was, frankly, one of the few serious scientists in the world who thought sleep was worth dedicating a career to. Most of the scientific establishment at the time considered sleep a pretty boring topic. The brain shuts down, you're unconscious for a while, you wake up. What's to study? Kleitman disagreed. He thought sleep was an active process, not just the absence of wakefulness, and he'd been looking for ways to prove it. Oserinsky's job was to observe sleeping subjects and record their eye movements using a device called an electrooculogram, which measures the tiny electrical signals produced when your eyes move. And what Oserinsky noticed was something no one had documented before. At certain points during the night, the sleeper's eyes would start moving rapidly back and forth beneath their closed eyelids. Not the slow, rolling movements you see when someone is drifting off. These were quick, darting movements, almost like the person was watching a tennis match with their eyes closed. And when Oserinsky woke the subjects up during these periods of rapid eye movement, they almost always reported vivid, detailed, story-like dreams. When he woke them during other periods of sleep, they rarely reported dreams, or if they did, the dreams were vague and fragmentary. This was the discovery of REM sleep, rapid eye movement sleep, and it was published in 1953 in the journal Science. And it changed everything, because suddenly dreams weren't just subjective reports that you had to take on faith. They were tied to a measurable, observable, physiological state. You could see dreaming happening from the outside. You could watch someone's eyes flickering, look at their brain waves on an electroencephalogram and say with reasonable confidence, this person is dreaming right now. And here's what made it even more fascinating. When Oserinsky and Kleitman looked at the brainwave patterns during REM sleep, they found something nobody expected. The brain wasn't quiet. It wasn't in some low-power standby mode. The electrical activity during REM sleep looked almost identical to the brain activity of someone who was wide awake. The brain was buzzing, firing, processing. It was, by every electrical measure they had, fully active. And yet the person was deeply asleep, essentially paralyzed, unresponsive to the outside world. This was such a striking paradox that a French researcher named Michel Jouvet, working independently in Lyon in the late 1950s, coined a term for it that stuck. He called REM sleep paradoxical sleep, sommeil paradoxal, because it was exactly that, a paradox. The brain of a dreamer is one of the most active brains you'll ever measure, wrapped inside a body that can barely move a muscle. And the reason for that paralysis, it turns out, is one of the most clever and slightly terrifying pieces of biological engineering your body performs every single night, which is something we should really talk about, because when that system fails, the results are genuinely unsettling. Because what we're talking about here is a condition called REM atonia, and it's something your brainstem orchestrates with remarkable precision every time you slip into a dream. Here's how it works. During REM sleep, a cluster of neurons in the pons, that's a structure deep in your brainstem, one of the oldest parts of your brain in evolutionary terms, sends signals down through the spinal cord that effectively shut off your voluntary muscles. Not your diaphragm, thankfully, so you keep breathing. Not your heart, obviously. But the big skeletal muscles, the ones that move your arms and legs and torso, they get chemically inhibited. The neurotransmitters glycine and GABA flood the motor neurons and essentially tell them to stand down. You're locked in place. And the reason your body does this is beautifully logical when you think about it. If your brain is going to generate vivid, realistic experiences, running, fighting, falling, swimming, whatever your dream happens to involve, and if your motor cortex is going to fire as though those actions are really happening, which it does, then you need some kind of safety mechanism to prevent your body from actually acting all of that out. Imagine dreaming you're sprinting through a forest and your legs actually start running while you're lying in bed. You'd hurt yourself. You'd hurt anyone sleeping next to you. You'd roll off the bed, crash into furniture, walk into walls. So evolution solved this problem in the most elegant way possible. It disconnects the motor output. Your brain dreams of running, and the signals travel down toward your muscles, but they get intercepted and blocked before they arrive. The engine revs, but the transmission is in neutral. Now here's what happens when that system breaks down. There's a condition called REM sleep behavior disorder, or RBD, and it's exactly what it sounds like. The paralysis mechanism fails, partially or completely, and people start physically acting out their dreams. They punch, they kick, they shout, they leap out of bed. And because they're still asleep, still dreaming, they have no awareness of what they're doing in the real world. The injuries can be serious. Broken bones, lacerations, sometimes injuries to bed partners. It was first formally described as a clinical disorder in 1986 by a researcher named Carlos Schenk and his colleague Mark Mahowald at the University of Minnesota. They documented a series of patients, mostly older men, who were presenting with violent sleep behaviors, and when they brought these patients into the sleep lab and monitored them, the findings were clear. During REM sleep, the normal muscle atonia was absent. The brainstem wasn't doing its job. The disconnect between brain and body had been lost. And here's something that makes RBD even more medically significant, and honestly a little sobering. Researchers discovered over the following decades that RBD is strongly associated with neurodegenerative diseases, particularly Parkinson's disease, and a related condition called Lewy body dementia. In many cases, RBD appears years or even decades before any other symptoms of neurodegeneration show up. Some studies suggest that more than 80% of people diagnosed with RBD will eventually develop one of these conditions. So in a strange and somewhat heartbreaking way, the failure of your dream paralysis system can be an early warning sign that something is going wrong in the deeper structures of your brain, long before tremors or cognitive decline become apparent. The neurons that maintain REM atonia are among the first casualties of these diseases, and their loss shows up in the sleep lab before it shows up anywhere else. But let's step back from the clinical side for a moment, because there's a flip side to this paralysis story that you've probably experienced yourself, and it's one of the most common and most distressing sleep phenomena out there. It's called sleep paralysis, and it's essentially the opposite problem. Instead of the paralysis failing when it should be active, the paralysis persists when it should have switched off. You wake up. Your consciousness comes back online. Your eyes open. You're aware of your bedroom. But your body is still locked in REM atonia. You can't move. You can't speak. You might be able to wiggle a finger or a toe, but your limbs feel impossibly heavy, pinned to the mattress by some invisible force. And because your brain is still partially in REM mode, still generating dream content, you might hallucinate. People report seeing dark figures in the room, feeling a weight on their chest, sensing a malevolent presence nearby. It's terrifying, and it has been terrifying people for centuries. Think about what that experience would have meant to someone in the Middle Ages. You wake in the dark, unable to move, and you see a shadowy figure sitting on your chest. Of course you'd think it was a demon. Of course you'd think you were being visited by something supernatural. The word nightmare itself traces back to this experience. The mare in nightmare refers to a mara, an Old English and Germanic term for a malevolent spirit that was believed to sit on your chest while you slept. There's a famous painting by Henry Fuseli from 1781 called The Nightmare that depicts exactly this. A woman draped across a bed with a demonic creature crouched on her torso, and a ghostly horse's head peering through the curtains. It's one of the most iconic images in Western art, and it's essentially a painting of sleep paralysis. The incubus on the chest, the sense of dread, the inability to move. Fuseli captured it perfectly, even if he didn't know the neuroscience behind it. And the thing is, sleep paralysis isn't rare. Surveys suggest that somewhere between 8 and 30% of people experience it at least once in their lives, with higher rates among students, people with disrupted sleep schedules, and those who sleep on their backs. It's more common than most people realize, and it's completely harmless. Your body is just a little slow to release the paralysis after your mind wakes up. It usually lasts only a few seconds to a couple of minutes, though it can feel much longer when you're in the middle of it. Knowing what it is, knowing the mechanism, doesn't necessarily make it less frightening in the moment, but it does strip away the supernatural dread. You're not being visited by demons. Your brainstem is just slightly out of sync with your cortex. The timing is off by a few beats, and your conscious mind wakes up before the all-clear signal reaches your muscles. So now we have this picture of REM sleep as this extraordinary state. The brain fully active, the body fully paralyzed, the eyes darting around as though watching something, and the mind immersed in experiences that feel completely real. But here's a question that started nagging researchers almost immediately after Oserinsky and Kleitman's discovery. Why? What is the brain actually doing during all of this? What is the purpose of dreaming? Because from an evolutionary standpoint, REM sleep is expensive. It consumes almost as much energy as being awake. It leaves you vulnerable. You're unconscious. You're paralyzed. You can't respond to threats. Every mammal that's been studied appears to have REM sleep, and birds do too, which suggests it evolved a very long time ago and has been conserved across species because it does something important enough to justify the cost. So what is it? This is where things get really interesting, because the honest answer is that after more than 70 years of research since the discovery of REM sleep, there still isn't a single, universally accepted theory of why we dream. There are several strong theories, and they're not all mutually exclusive. Dreams might serve multiple functions simultaneously. But the debate is very much alive. And the history of that debate tells you a lot about how science works when the thing you're studying is, by its very nature, private, subjective, and maddeningly difficult to pin down. The first major post-Freudian theory came in 1977, and it was deliberately, almost provocatively, anti-Freudian. Two Harvard psychiatrists, J. Allen Hobson and Robert McCarley, proposed what they called the activation synthesis hypothesis, and the core idea was radical in its simplicity. They argued that dreams don't originate from hidden psychological meanings or repressed desires. Instead, dreams begin as essentially random neural activity. During REM sleep, the pons, that same brainstem structure involved in triggering the paralysis, sends random electrical signals up into the cortex, the higher brain. These signals activate various regions involved in vision, emotion, movement, memory, and the cortex, being the meaning-making machine that it is, tries to make sense of all this random input. It takes the noise and weaves it into a narrative. It synthesizes a story. That's the dream, not a message from your unconscious, not a coded wish, just your cortex doing what it always does, finding patterns, constructing coherent experience. Except this time, the raw material is random internal noise instead of organized sensory input from the outside world. Hobson was blunt about this. He essentially said that dreams are meaningless at their origin. They're the brain's attempt to impose order on chaos. The reason dreams are bizarre, he argued, is because the input is bizarre. Random neurons firing in random patterns produce random imagery, and the cortex does its best to stitch it together. But the seams show. That's why dreams jump from scene to scene, why people transform into other people, why the logic is fluid and the geography is impossible. The cortex is working with bad data and doing a remarkably creative job under the circumstances, but it can't produce a coherent narrative from incoherent input. Now, you can imagine how this went over. Freudians were appalled. Hobson was essentially saying that a century of dream interpretation was built on a false premise, that there was nothing to interpret, no hidden meaning to decode, just neural static dressed up in narrative clothing. But the activation synthesis model had something powerful going for it. It was testable. It made specific predictions about brain activity during REM sleep that could be checked with the emerging tools of neuroimaging. And some of those predictions held up beautifully. But others didn't. And over the following decades, the picture got more complicated, because researchers started finding evidence that dreams weren't quite as random as Hobson initially proposed. There were patterns. There were recurring themes tied to waking concerns. There was emotional consistency. And there was one particular set of experiments involving rats and a maze that suggested dreams might be doing something far more purposeful than anyone in the activation synthesis camp had imagined, something that connects directly to how your brain learns and remembers things, and that's where the story gets really fascinating. So picture this. It's the year 2001, and a neuroscientist named Matthew Wilson at MIT is working with rats. Now, Wilson had been doing something remarkably clever for years at this point. He and his colleague Bruce McNaughton, back in 1994, had developed a technique where they could record from large numbers of individual neurons in a rat's hippocampus simultaneously. The hippocampus, and we'll come back to this structure a lot, is this curved, seahorse-shaped region deep in the brain that's absolutely critical for forming new memories. It's essentially your brain's recording studio, the place where experiences get laid down before they're eventually consolidated and distributed to longer-term storage elsewhere. And what Wilson could do was listen to these hippocampal neurons while the rat was running through a maze during the day, and he could identify specific firing patterns, particular sequences of cells lighting up in a particular order that corresponded to specific locations in the maze. Think of it like each spot in the maze has its own neural signature, its own little melody played by a specific combination of neurons. So as the rat runs from point A to point B to point C, you get this sequence of neural melodies playing in order, and Wilson could read that sequence and essentially know where the rat was in the maze just by listening to its brain. Here's where it gets wild. Wilson then recorded from those same neurons while the rat slept afterward, and what he found was that during REM sleep, those exact same firing sequences replayed, the same neurons, firing in the same order, at roughly the same temporal relationships to each other. The rat's hippocampus was essentially running through the maze again, replaying the experience of navigating that space, but while the rat was lying still in its cage with its eyes closed. The patterns were so precise that Wilson could actually determine which part of the maze the rat was dreaming about at any given moment. Now think about what that means. If dreams were truly just random noise, just the cortex trying to make sense of chaotic Pontine signals, you wouldn't expect to see this kind of structured, experience-specific replay. You'd expect garbled, disordered firing. But that's not what was happening. The replay was orderly. It was sequential. It was tied directly to what the rat had actually done during the day. And it wasn't just a one-time fluke. Wilson and his team found this consistently, across many rats, across many sessions. The brain was rehearsing. And here's the kicker. The replay wasn't just a passive echo. Subsequent work showed that this replay was actually important for learning. Rats that got more of this replay during sleep performed better on the maze the next day. Their performance improved overnight in ways that correlated with the amount and fidelity of hippocampal replay during sleep. Disrupt that sleep, and the improvement disappeared. The rats that were woken up during REM, or that had their hippocampal replay interfered with, didn't consolidate the spatial memory as effectively. Something was happening during that replay that was functionally important. The brain wasn't just idly revisiting the day's events. It was actively processing them, strengthening the neural connections that encoded the correct path through the maze. Now, you might be thinking, okay, but those are rats. Rats running through mazes. How much can we really extrapolate from that to human dreaming? And that's a fair question. But here's the thing. The basic architecture is remarkably conserved. Humans have hippocampi that work on very similar principles. We have place cells and spatial mapping systems that operate the same way. And when researchers started looking for similar replay phenomena in humans, they found them. One of the most elegant demonstrations came from a study by Aaron Walmsley and Robert Stickgold at Harvard, published around 2010. They had people learn to navigate a virtual maze, a three-dimensional computer environment, and then took naps. Some of the subjects reported dreaming about the maze, and the ones who dreamed about it showed significantly more improvement on the task when they woke up compared to those who didn't dream about it. The dreaming itself seemed to be a marker of, or possibly a mechanism for, the memory consolidation process. Now, the dreams weren't exact replays of the maze the way the rat hippocampal patterns were. The human dreams were more fragmented, more associative. Someone might dream about the maze, but with different people in it, or the maze might be outdoors instead of on a computer screen, or they might dream about a maze-like structure from their childhood that the task reminded them of. The cortex was doing its thing, weaving associations, pulling in related memories, but the core spatial learning was being processed. And this connects to something you've probably experienced yourself. You ever struggle with a problem all day? Maybe you're trying to learn a new route through a city, or you're working through some complicated task at work, or you're practicing a musical instrument, and then you sleep on it, and the next day it just feels easier. That's not folk wisdom. That's real. That's measurable. And a significant body of research now suggests that sleep, and specifically the dreaming phases of sleep, play a genuine role in that overnight improvement. So this was a real challenge to the pure activation synthesis model. Hobson's original framework said dreams are the cortex making stories from random noise. But the replay data suggested the input wasn't random at all. It was structured, it was experience dependent, and it was functionally connected to learning. To his credit, Hobson revised his model over the years. By the early 2000s, he and his colleagues had developed what they called the AIM model. That stands for activation, input source, and modulation, which was more nuanced, acknowledging that the brain's state during REM involves specific neurochemical conditions that might facilitate certain kinds of cognitive processing. He moved away from the dreams are meaningless position toward something more like dreams are a different mode of cognition, which is a pretty significant shift when you think about it. But let's talk about what's actually happening chemically during REM sleep, because this matters a lot for understanding why dreams feel the way they do and what they might be accomplishing. During REM, your brain's neurochemical environment is dramatically different from waking life. Specifically, two neurotransmitters that are very active during the day essentially shut down during REM. Norepinephrine, which is involved in focused attention and logical reasoning, drops to near zero, and serotonin, which is involved in mood regulation and impulse control, also drops to very low levels. Meanwhile, acetylcholine, which is involved in memory processing and sensory vividness, surges to levels that are actually higher than during waking. So think about what that cocktail produces. You've got a brain that is highly activated, highly capable of vivid sensory experience and memory access, but almost completely lacking in the neurochemistry of logical reasoning and focused attention. That's why dreams feel so real while you're in them, but so illogical when you wake up and try to reconstruct them. During the dream, you don't have the norepinephrine-driven critical thinking that would let you say, "Wait, I can't fly. This doesn't make sense. I'm dreaming." Your brain is running without its fact-checker. The editorial department has gone home for the night, but the creative department is working overtime. And here's what's really clever about this from a functional standpoint. Some researchers, notably Sarah Mednick at UC Irvine and others, have proposed that this particular neurochemical state is actually ideal for a specific kind of cognitive work: finding distant associations. During the day, your norepinephrine-rich brain is great at focused, logical, step-by-step reasoning. But it's not as good at making loose, creative connections between seemingly unrelated ideas. The REM brain, stripped of norepinephrine but flooded with acetylcholine, is essentially running in a different mode, one that's optimized for finding hidden patterns, for connecting things that your waking mind would never put together. And there's evidence for this. Studies have shown that people are better at solving creative problems, anagram puzzles, remote association tasks, insight problems, after REM sleep compared to equivalent periods of waking, or even compared to non-REM sleep. It's as if the dreaming brain is running a kind of defragmentation program. But instead of just organizing files, it's looking for connections between files that you didn't know were related. This might explain one of the most romantic traditions in the history of science and engineering, the breakthrough that comes in a dream. You've probably heard some of these stories. August Kekulé, the German chemist, claimed that the ring structure of benzene came to him in a dream about a snake biting its own tail, the Ouroboros, sometime around 1865. Now, historians have debated how literally true that account is, and Kekulé himself told the story decades after the fact, so the details may have been polished. But the underlying principle is sound. Kekulé had been struggling with how 6 carbon atoms could arrange themselves in a stable molecule, and the conventional linear chain models weren't working. His brain had all the pieces, years of chemical knowledge, the constraints of the problem, the failed approaches, and during sleep, freed from the tyranny of logical sequential thinking, it found the pattern. A ring, a closed loop. It was a leap that linear reasoning had failed to make. Dmitri Mendeleev reportedly saw the arrangement of the periodic table in a dream in 1869. Elias Howe, the sewing machine inventor, is said to have solved the problem of needle design through a dream about spears with holes in their tips. Whether these specific dream accounts are perfectly accurate or somewhat mythologized, the cognitive principle they illustrate is well supported by modern research. The sleeping brain, particularly during REM, is doing real work, finding real connections, solving real problems. But here's where we need to be careful, because there's a temptation to swing too far in the other direction, to go from dreams are meaningless noise, all the way to dreams are profound messages from your subconscious that you need to decode. The truth, as it usually does, lives somewhere in the messy middle. Dreams reflect your brain's ongoing processing of experience, emotion, and memory. They are shaped by what you've been doing, what you're worried about, what you're trying to learn. But they're not coded messages. They're not prophecies. They're more like, and this is an analogy I really like, they're more like watching your brain think out loud in a language that isn't quite English. You can catch fragments of meaning. You can see the themes, but trying to build a precise dictionary of dream symbols, the way Freud wanted to, is probably a dead end. And that brings us to something we haven't really talked about yet, the emotional dimension of dreams, which might be the most important piece of the puzzle. Because when researchers actually catalog what people dream about, what shows up most consistently isn't random imagery, it's emotion, specifically negative emotion. Dreams are disproportionately anxious, threatening, and stressful compared to waking life. Studies by Calvin Hall, who collected over 50,000 dream reports starting in the 1940s, and later by Antti Revonsuo at the University of Turku in Finland, have consistently shown that the emotional tone of dreams skews negative. People dream about being chased, about failing, about social embarrassment, about losing things, about being unprepared. The classic showing up to an exam you didn't study for dream. The falling dream, the being chased dream. These aren't just cliches. They show up in the data with remarkable consistency across cultures and across decades of dream research. And Revonsuo, in the year 2000, proposed something really interesting to explain this pattern, something he called the threat simulation theory. His idea was that dreaming evolved primarily as a kind of virtual reality threat rehearsal system. Your brain, during sleep, runs simulations of dangerous or challenging scenarios so that you'll be better prepared to handle them if they occur in waking life. It's like a flight simulator for survival. You practice fleeing from predators, navigating social conflicts, responding to emergencies, all in the safety of your own skull, with your muscles paralyzed so you can't actually hurt yourself. And the reason negative emotions dominate dreams is because those are the scenarios where rehearsal matters most. You don't need to practice lying on a beach. You need to practice what happens when something goes wrong. Now, this is a beautiful theory, and it has some compelling evidence behind it, but it also has some significant problems, and the debate it sparked connects to an even deeper question about what dreams are actually for, whether they're for anything at all, in a functional sense, or whether they're just a byproduct of something else the sleeping brain is doing. So let's dig into the problems with threat simulation theory, because they're instructive. The first issue is specificity. If dreams evolved primarily to rehearse threats, you'd expect the content of dreams to be pretty tightly focused on realistic, survival-relevant dangers, the kind of threats our ancestors actually faced on the savannah. Predator attacks, hostile encounters with rival groups, falling from heights, navigating treacherous terrain. And yes, some dreams do feature those things, but a huge number of dreams involve scenarios that have absolutely nothing to do with physical survival. You dream about showing up late to a meeting. You dream about your teeth falling out. You dream about an ex-partner from 15 years ago showing up at a dinner party with someone you don't recognize. You dream about trying to use a phone that won't work, or wandering through a building with hallways that don't make sense. These are stressful, sure. They're emotionally charged. But they're not exactly the kind of threat rehearsal that would have given our Pleistocene ancestors a survival edge. Ravensua would argue that the system has been co-opted, that it originally evolved for genuine physical threats, but has been repurposed by modern brains to simulate modern anxieties. And that's a reasonable response, but it starts to stretch the theory thin. Once you allow that, the system can simulate any kind of anxiety, not just survival-relevant threats. You've broadened the claim so much that it becomes hard to falsify. It's no longer really a threat simulation theory. It's an anxiety simulation theory. And at that point, you have to ask, is this really an evolved function? Or is it just what happens when an emotional brain generates narratives while the logical prefrontal cortex is turned way down? Here's the second problem. If threat simulation dreams were genuinely functional, if they actually improved your ability to respond to dangers, you'd expect to find clear evidence that people who dream more about threats perform better when facing real ones. And that evidence is surprisingly thin. There are some suggestive findings. Ravensua and his colleagues found that people who had experienced real trauma tended to have more threat-related dreams, which you might interpret as the system working harder when it's most needed. But having more threat dreams after trauma could just as easily be a symptom of distress rather than a functional rehearsal process. People with PTSD have intensely threatening dreams, the same nightmare, sometimes, over and over. And those dreams don't seem to help them cope better. If anything, the repetitive nightmares of PTSD seem to make things worse, not better. They disrupt sleep, they increase daytime anxiety, and they're one of the most distressing symptoms of the disorder. That's a real challenge for threat simulation theory. If the system is supposed to help you prepare for threats, why does it seem to malfunction so badly in exactly the people who need it most? And this brings us to a competing idea about dream emotionality that came from a very different angle. In the early 2000s, a neuroscientist named Matthew Walker, you may have heard of him, he later wrote the best-selling book Why We Sleep, was working at Harvard and then at UC Berkeley. and he became deeply interested in the relationship between REM sleep and emotional processing, not threat simulation specifically, but something broader. Walker proposed that REM sleep serves as a kind of overnight therapy session. The idea goes like this. During the day, you experience things that carry emotional weight: an argument with a friend, an embarrassing moment at work, a piece of bad news, a close call in traffic. These experiences get encoded in memory along with the emotions attached to them. And during REM sleep, your brain replays those memories, but it does so in a very particular neurochemical environment. Remember how we talked about norepinephrine, that stress-related neurotransmitter that drops to nearly zero during REM? Walker argued that this is the key. When your brain reprocesses emotional memories during REM sleep, it does so in a state where the chemical signature of stress has been stripped away. So the memory gets consolidated. You remember what happened, but the emotional sting gets gradually dulled. You wake up and the memory is still there, but it doesn't hurt as much. The edge has been taken off. Think about that for a second. You've probably experienced this yourself. Something happens that feels devastating in the moment. You say the wrong thing in a conversation. You get some criticism that cuts deep. You have a fight with someone you care about. And that night, it's all you can think about. But then you sleep on it, and in the morning it's still there, but it feels different, more manageable, less raw. Give it time, people say. Sleep on it. And Walker's argument is that this isn't just folk wisdom. It's describing a real neurobiological process. REM sleep is literally stripping the emotional charge from your memories, reprocessing them in a safe, low-stress chemical bath so that by morning you can think about what happened without being overwhelmed by how it felt. And here's where it connects beautifully to what we know about the dreaming brain. The dreams you have during REM often involve emotional content from your recent waking life, but scrambled, recombined, placed in unfamiliar contexts. You dream about the argument, but it's happening in your childhood kitchen, and the person you're arguing with keeps shifting identity. Walker suggested that this recombination isn't random noise. It's part of the therapeutic process. By replaying the emotional core of an experience in different narrative contexts, your brain is essentially decoupling the emotion from the specific triggering event. It's learning that the feeling of anxiety or shame or fear isn't welded to that one particular memory. It can arise in other contexts, and it can be survived. The emotional memory gets integrated into your broader understanding of the world, rather than sitting there as an isolated, charged, painful thing. Now, Walker and his colleagues ran some elegant experiments to test this. In one study, published around 2011, they showed participants a set of emotionally provocative images, things designed to elicit strong reactions, and then tested their emotional responses to the same images 12 hours later. One group saw the images in the morning and was tested that evening, staying awake all day. The other group saw them in the evening and was tested the next morning after a full night of sleep. The group that slept showed significantly reduced emotional reactivity to the images. Their brains, when scanned with fMRI, showed less amygdala activation. The amygdala being that almond-shaped structure deep in the brain that acts as a kind of emotional alarm system. And critically, the reduction in emotional reactivity was correlated with the amount of REM sleep the participants got, and specifically with how much their norepinephrine levels dropped during REM. The lower the norepinephrine during REM, the better the overnight emotional processing. This is a really satisfying result because it ties together so many threads. It explains why dreams are emotional, It explains why they often feature distorted versions of recent experiences. It explains why REM sleep specifically, with its unique neurochemistry, is the stage that matters for this process. And it offers a mechanistic account of something we all intuitively know, that sleeping on a problem helps. But, and you knew there was going to be a but, this theory has its own complications. The biggest one is PTSD, and it's actually the same problem that plagues threat simulation theory. If REM sleep is supposed to strip the emotional charge from difficult memories, why doesn't it work for people with PTSD? Why do they keep having the same horrible dream, with the same horrible emotional intensity, night after night? Walker's answer is interesting. He suggested that in PTSD, the norepinephrine system is broken. People with PTSD have elevated norepinephrine levels even during sleep. Their stress chemistry doesn't turn off the way it's supposed to. So when their brains try to reprocess the traumatic memory during REM, the norepinephrine is still there, and the emotional charge doesn't get stripped away. The memory gets replayed with its full emotional intensity, which is re-traumatizing rather than therapeutic, which elevates stress further, which keeps norepinephrine high, which prevents the next night's processing from working either. It's a vicious cycle, and this actually aligns with a clinical observation. One of the medications that's been found to help with PTSD nightmares is prazosin, which is a drug that blocks norepinephrine receptors. Prazosin was originally developed as a blood pressure medication, but clinicians noticed that veterans taking it reported fewer nightmares and better sleep. And Walker's framework explains why. By blocking norepinephrine during sleep, prazosin restores the neurochemical conditions needed for proper emotional processing. The overnight therapy can finally work. That's a compelling story. It's the kind of thing where the clinical data and the neuroscience and the subjective experience all seem to line up. But we should be careful, because the history of dream science is littered with beautiful theories that turned out to be incomplete. And Walker's overnight therapy model, while influential, has faced criticism on several fronts. Some researchers have pointed out that the evidence for emotional processing during sleep isn't as clean as the initial studies suggested. Replication has been mixed. The relationship between REM sleep and emotional memory is real, but it may not be as straightforward as the theory implies. Other sleep stages seem to matter too. And the idea that dreams themselves, the subjective experience, the narrative, are doing the therapeutic work, as opposed to the underlying neural processes that happen to produce dreams as a side effect, remains genuinely unresolved. And this is where we arrive at one of the deepest divides in dream science, a question that has been lurking beneath everything we've talked about so far. Are dreams functional? Do they do something? Or are they epiphenomenal, a word that basically means they're the exhaust, not the engine? When your brain consolidates memories during sleep, when it strips emotional charge from difficult experiences, when it replays neural sequences from the day's learning, does the dream itself, the subjective movie playing in your head, actually matter? Or would all of that processing happen just the same, even if you experienced nothing? Even if the screen was dark? This is a surprisingly hard question to answer, and it connects to some of the deepest problems in consciousness research more broadly. But there's a fascinating line of evidence that bears on it, and it comes from a technique that lets researchers do something that would have seemed like science fiction just a few decades ago. It lets them communicate with people who are actively dreaming. The technique is called lucid dreaming, and the research that's been done with it, particularly by a group in Germany and another in the United States and France working together in the early 2020s, has started to crack open questions that dream science had been circling around for decades. So let's talk about what they actually did. Lucid dreaming itself isn't new. People have known about it for a very long time. The term was coined by a Dutch psychiatrist named Frederick van Eden back in 1913, and he described it as a dream in which you know you're dreaming while it's happening. You're asleep, you're in a dream. But some part of your awareness kicks in and says, wait, this isn't real. I'm dreaming right now. And for most of the 20th century, mainstream sleep science didn't take it very seriously. It sounded too mystical, too subjective, too much like something you'd hear about at a meditation retreat rather than in a neuroscience lab. The problem was obvious. How do you study something that's entirely inside someone's head during a state where they can't talk to you? But then a psychophysiologist named Stephen LaBerge, working at Stanford in the late 1970s, figured out something clever. He realized that even though most of your muscles are paralyzed during REM sleep, remember the atonia we talked about, Jouvet's cats, the brainstem mechanisms that keep you from acting out your dreams, your eye muscles aren't. Your eyes still move during REM. That's literally what gives REM sleep its name. So LaBerge trained himself to become lucid in his dreams, and then, once lucid, to move his eyes in a specific prearranged pattern. Left, right, a deliberate signal, like Morse code sent from inside the dream. And in 1981, he published a paper showing that these eye movement signals could be detected on the polysomnograph, the same machine that records sleep stages. The signals appeared right in the middle of unambiguous REM sleep. It was the first objective proof that lucid dreaming was real, that a person could be verifiably asleep, verifiably in REM, and simultaneously aware enough to send a deliberate signal to the waking world. Think about what that means for a second. It's a communication channel between a dreaming mind and the outside world. A tiny one, sure, just eye movements. But it was real, and it was verified, and it opened a door that nobody had been able to open before. Now, LaBerge's work was groundbreaking, but it had limitations. The communication was one way. The dreamer could signal out, but researchers couldn't easily signal in, and the whole thing depended on the dreamer becoming lucid spontaneously or through training, which is unreliable. Most people rarely have lucid dreams, and even experienced lucid dreamers can't always trigger them on demand. So for decades, lucid dreaming research remained a niche field, respected by those who worked in it, but not central to the big questions in sleep science. And then, in 2021, a paper came out that changed things. It was published in Current Biology, and it was a collaboration between 4 independent labs, one in Germany led by Christopher Appel and Martin Dressler, one in the United States led by Ken Powler at Northwestern, one in France led by Delphine Oudiet, and one in the Netherlands. And what they showed was that two-way communication with dreaming people was possible, not just the dreamer signaling out, but the researcher asking questions and the dreamer answering them in real time while remaining asleep and in a verified dream state. Here's how it worked. They would wait for a participant to enter REM sleep and become lucid, confirmed by the prearranged eye movement signal. Then the researchers would pose simple questions. Sometimes these were spoken aloud, sometimes delivered as flashing lights or taps on the hand. Things like basic math problems. What's 8 minus 6? And the dreamers would answer using eye movements or facial muscle contractions, signals they'd practiced beforehand. And they got correct answers. Not always, not perfectly, but well above chance. In the Northwestern experiments, for instance, dreamers correctly answered math questions, and yes or no questions while remaining in REM sleep, and some of them later reported that the questions had been incorporated into their dreams. One participant described hearing the math problem as if it came from a car radio inside the dream. Another said it felt like a narrator's voice, like a voiceover laid on top of the dream scene. Now, you might be thinking, okay, that's cool. But is it really that different from what LaBerge did? And the answer is yes, fundamentally. Because LaBerge showed that dreamers could send signals out. This showed that information could go both ways, that a sleeping, dreaming brain could receive novel external information, process it, compute a correct answer, and communicate that answer back, all without waking up. That's not just awareness. That's cognitive processing. That's something much closer to what we'd normally call consciousness. And this is where it connects back to the question we were sitting with, whether dreams are functional or epiphenomenal. Because if a dreaming brain can do math, can receive and process new information, can make deliberate decisions about how to respond, then the dream state isn't just neural noise that happens to produce hallucinations as a byproduct. There's somebody home. There's a mind in there, doing things. And that makes it much harder to argue that the subjective experience of dreaming is irrelevant to whatever functions sleep is performing. But here's the thing. It doesn't prove that dreams are functional either. It proves that consciousness persists during dreaming, at least during lucid dreaming. But lucid dreaming is unusual. It's a modified state. Critics have pointed out, reasonably, that lucid dreaming might not be representative of ordinary dreaming at all. When you become lucid, your prefrontal cortex, the part of the brain responsible for self-awareness, planning, rational thought, all the things that are normally suppressed during REM, partially reactivates. Brain imaging studies by Dressler and others have shown increased activity in the dorsolateral prefrontal cortex during lucid REM, which is precisely the region that's quiet during normal dreaming. So in a sense, lucid dreaming is a hybrid state. It's not fully awake and it's not fully dreaming. It's something in between. And that means you can't necessarily generalize from lucid dreams to all dreams. Still, the research has opened up possibilities that didn't exist before. Imagine being able to ask someone while they're dreaming what they're experiencing. Imagine being able to test whether manipulating dream content changes the functional outcomes of sleep. Does dreaming about a task improve performance more than sleeping without dreaming about it? These are experiments that are now, in principle, possible. They're incredibly difficult to run because inducing lucid dreams reliably is still a major challenge, and maintaining two-way communication long enough to do meaningful experiments is even harder. But the door is open, and the work connects to another thread that's been running through dream science for years: the question of dream content. We talked about Calvin Hall's massive database of dream reports, and Ravon Suo's threat simulation theory, and Walker's emotional processing model. All of these theories make claims about what dreams are about and why they're about those things. But testing those claims has always been limited by the fact that dream reports are retrospective. You wake someone up and ask them what they were dreaming, and you're relying on their memory, which is notoriously unreliable for dreams. Most dream content evaporates within minutes of waking. What you remember is a reconstruction, shaped by the act of waking up, by your expectations, by the questions the researcher asks you. It's like trying to study a live performance by interviewing audience members the next morning. Lucid dreaming research offers a way around this, at least partially. A lucid dreamer can, in theory, report on dream content as it's happening, flagging when a threatening scenario appears, or when an emotional memory surfaces, or when the dream shifts from one scene to another. It's not perfect. The act of monitoring and reporting changes the dream, just as observing a quantum system changes it. But it's closer to real-time data than anything we've had before. So where does all of this leave us on the big question? Are dreams functional? Honestly, as of the mid-2020s, the field is still genuinely divided. There are serious researchers who believe that dreams, the subjective narratives, the felt experience, serve real purposes. Memory consolidation, emotional regulation, creative problem solving, threat rehearsal, some combination of these. And there are equally serious researchers who think that the important work happens at the neural level, in the firing patterns and chemical environments of sleeping brain tissue, and that dreams are just what it feels like from the inside when that machinery runs. The exhaust, not the engine. And maybe, and this is a thought worth sitting with, maybe the question itself is a bit like asking whether the redness of a sunset is functional. The sunset is caused by the scattering of light through the atmosphere, and that scattering has physical consequences. It affects how much ultraviolet radiation reaches the ground. It influences temperature gradients. It matters for all sorts of atmospheric processes. But the redness, the subjective experience of seeing red, does that do anything? Or is it just what it's like to have eyes and a visual cortex pointed at scattered light? The hard problem of consciousness, as the philosopher David Chalmers called it in 1995, is essentially this question applied to all subjective experience. And dreams sit right at the heart of it, because they're subjective experiences that occur in the absence of external input, generated entirely from within. But let's set the philosophy aside for a moment, because there's a much more practical dimension to all of this that affects millions of people, and it has to do with what happens when dreaming goes wrong in specific, diagnosable, treatable ways. We've already talked about REM sleep behavior disorder and sleep paralysis, but there's a whole landscape of dream-related clinical phenomena that intersect with psychiatry, neurology, and pharmacology in ways that are directly relevant to how we treat some of the most common conditions in medicine. Take antidepressants, for instance. SSRIs, selective serotonin reuptake inhibitors, drugs like fluoxetine, sertraline, paroxetine, are among the most widely prescribed medications on the planet. Hundreds of millions of prescriptions every year. And one of their most consistent effects on sleep is that they suppress REM. They reduce the amount of REM sleep you get, they delay the onset of your first REM period, and they often reduce dream recall. People on SSRIs frequently report that they dream less, or that their dreams become less vivid. Now, if REM sleep and dreaming are critical for emotional processing, if Walker's overnight therapy model is correct, then you'd expect SSRIs to impair emotional memory processing. And yet, for many people, SSRIs improve mood. They reduce anxiety. They help with depression. How do you square that? This is one of those puzzles that keeps sleep researchers up at night, no pun intended. One possibility is that SSRIs work through mechanisms that are completely independent of sleep, and the REM suppression is just a side effect that doesn't matter much. Another possibility is that the serotonin boost from SSRIs compensates for whatever emotional processing is lost by reducing REM, that you're getting the emotional regulation through chemistry rather than through sleep architecture. A third possibility, and this is the one that some researchers find most intriguing, is that the relationship between REM sleep and emotional health isn't linear. Maybe you don't need a lot of REM to get the benefits. maybe the quality of the REM you do get matters more than the quantity. Or maybe too much REM, particularly the kind of intense, emotionally charged REM that depressed people tend to have, is actually part of the problem rather than the solution. And there's evidence for that last idea. People with major depression tend to have altered sleep architecture in a very specific way. They enter REM sleep faster than healthy people. Their first REM period is longer and more intense, and they have more REM overall, particularly in the first half of the night. This has been known since the 1970s, when researchers like David Kupfer at the University of Pittsburgh documented it. And one of the oldest and most robust findings in biological psychiatry is that sleep deprivation, specifically depriving someone of sleep for an entire night, can temporarily lift depression in about 60% of patients. The effect is dramatic and fast, much faster than any antidepressant drug. But it's also temporary. As soon as the person sleeps again, the depression typically returns. And when researchers looked at what aspect of sleep deprivation was doing the heavy lifting, they found that selectively depriving people of REM sleep produced similar antidepressant effects. So here's the paradox. REM sleep seems to be important for emotional processing and mental health. But too much REM, or the wrong kind of REM, might actually sustain depression, and drugs that suppress REM can treat depression. It's as if the system needs to be in a Goldilocks zone, enough REM to do its work, but not so much that it becomes a kind of echo chamber for negative emotion. And that idea, that metaphor of a Goldilocks zone, is one of the most useful ways to think about what modern sleep science is wrestling with right now, because it reframes the whole question. Instead of asking whether REM sleep is good or bad for you emotionally, which is too blunt a question, it asks, what does healthy REM look like? And what happens when the system drifts out of balance? Let's sit with the pharmacology for a moment, because it tells us something really important about how little we still understand. SSRIs, selective serotonin reuptake inhibitors, drugs like fluoxetine, sertraline, paroxetine, are the most widely prescribed antidepressants in the world. Hundreds of millions of people take them, and one of the most consistent things they do to sleep architecture is suppress REM. They delay its onset. They shorten REM periods. They reduce total REM time. Some patients on high doses of SSRIs lose the majority of their REM sleep. And yet these drugs help with depression. They help with anxiety. They help with OCD, with PTSD in some cases, with panic disorder. If REM sleep were simply essential for emotional regulation in a straightforward way, you'd expect that obliterating someone's REM would make them emotionally worse. But it doesn't, at least not in the ways you'd predict. Now, there are caveats. SSRI users do still get some REM. The suppression isn't total in most people, and there's some evidence that the REM they do get might be qualitatively different, perhaps more efficient, perhaps stripped of the kind of intense, ruminative emotional cycling that characterizes depressive REM. Nobody knows for sure. But the clinical reality is hard to argue with. Millions of people function well, feel better, and live full emotional lives on drugs that dramatically reduce their REM sleep. And that fact alone should make us humble about any simple story we try to tell about what dreams are for. Here's another wrinkle. MAOs, monoamine oxidase inhibitors, were among the earliest antidepressants developed in the 1950s. Drugs like phenelzine and tranylcypromine. They're powerful, they work for treatment-resistant depression, and they suppress REM sleep even more aggressively than SSRIs. There are documented cases of patients on MAOIs who showed virtually no measurable REM sleep on polysomnography for months, even years. And these patients didn't go psychotic. They didn't show catastrophic memory failures. They didn't fall apart emotionally. Some of them felt better than they had in years. Now, you might remember that early sleep deprivation studies, particularly the ones from the 1960s, suggested that depriving people of REM would lead to psychological disturbance. There was even talk of RM rebound causing hallucinations. But the MAOI data complicates that picture enormously. It suggests that the brain can adapt to very low levels of REM, at least when the suppression is pharmacological rather than forced. So, what do we make of all this? One possibility, and this is where some researchers have landed, is that REM sleep isn't a single thing with a single function. It's a complex brain state that does many things simultaneously: memory consolidation, emotional processing, synaptic homeostasis, maybe creative recombination. And the relative importance of each function might vary depending on the person, their current emotional state, their neurochemistry, and what's happened to them recently. When the system is working well, REM does its job quietly, and you wake up feeling okay. When the system is dysregulated, too much REM, too early, too emotionally intense, it can become part of the pathology rather than the cure. This brings us to something that clinicians deal with every day, but that doesn't always make it into the popular science books: nightmares. Not the occasional bad dream that everyone has, but chronic, recurrent, distressing nightmares that disrupt sleep and impair daytime functioning. Nightmare disorder, as it's formally called, affects somewhere between 2 and 8% of the general population, depending on how strictly you define it. And it's far more common in people with PTSD, depression, anxiety disorders, and borderline personality disorder. For some of these patients, nightmares aren't just a symptom, they're a maintaining factor. The dread of falling asleep, the hyperarousal that comes from waking in terror, the sleep fragmentation, the exhaustion. It creates a vicious cycle that keeps the underlying condition going. And here's what's fascinating from an engineering perspective, if you'll allow me to use that word loosely. The treatment that works best for chronic nightmares isn't a drug. It's a cognitive technique called imagery rehearsal therapy, or IRT, developed primarily by Barry Krakow in the 1990s and early 2000s. The idea is beautifully simple. You take the nightmare, the one that keeps recurring, and while you're awake during the day, you consciously rewrite it. You change the ending. You alter the threatening element. You don't have to make it happy, just different. And then you rehearse the new version in your mind, vividly, for 10 to 20 minutes a day. That's it. No dream journals during the night, no lucid dreaming techniques, no medication, just deliberate waking reimagination of the dream narrative. And it works. Multiple randomized controlled trials have shown that IRT significantly reduces nightmare frequency and intensity, improves sleep quality, and reduces PTSD symptoms. A landmark 2001 study by Krakow and colleagues, published in the Journal of the American Medical Association, showed that sexual assault survivors who practiced IRT had significantly fewer nightmares and better sleep 3 and 6 months later compared to controls. The effect sizes were large, and the therapy is brief, sometimes just 2 or 3 sessions. Think about what that implies. It means that the content of dreams, the narrative, the imagery, is not just random noise generated by a brainstem that's firing chaotically. If it were, you wouldn't be able to change it by rehearsing a different story while awake. The fact that IRT works suggests that dreams draw on the same cognitive and emotional schemas that operate during waking life. The mental models, the expectations, the narrative templates that your brain uses to predict and interpret experience. When you change the waking template, the dream follows. That's remarkable. It's almost as if dreams are a kind of simulation running on shared hardware, and you can update the software from the outside. This connects back to something we touched on earlier, Antti Revonsuo's threat simulation theory. If dreams really are a kind of rehearsal space, then it makes sense that the rehearsal would be influenced by waking experience and waking cognition. And it makes sense that a maladaptive rehearsal, one that's stuck in a loop, replaying the same threat without resolution, could be redirected by providing a new script. IRT isn't teaching the dreamer to lucid dream. It's not asking them to become conscious within the dream and take control in real time. It's doing something more subtle. It's reshaping the underlying template that the dreaming brain draws on when it constructs its nightly simulations. Now, there's another pharmacological approach to nightmares that's worth mentioning, because it circles back to the neurochemistry we talked about earlier. Prazosin. Remember prazosin? It's the alpha-1 adrenergic blocker that reduces norepinephrine signaling in the brain. It was originally a blood pressure medication, and its use for PTSD nightmares was discovered almost by accident in the late 1990s by Murray Raskind at the VA Puget Sound in Seattle. Raskind had a patient, a Vietnam veteran with severe PTSD nightmares, who happened to be taking prazosin for a urinary condition. The veteran mentioned offhandedly that his nightmares had stopped. Raskind, to his credit, paid attention. He started a small open-label trial, then a randomized controlled trial, and the results were striking. Prazosin significantly reduced trauma nightmares and improved overall sleep quality in combat veterans with PTSD. And the mechanism fits perfectly with what we discussed about REM neurochemistry. In healthy REM sleep, norepinephrine drops to near zero. That's part of what allows emotional memories to be reprocessed without the full stress response. The emotional tone gets filed away, but the visceral punch, the racing heart, the flood of adrenaline gets stripped out. In PTSD, norepinephrine stays elevated during REM. The system doesn't stand down, so when a trauma memory gets reactivated during dreaming, it comes with the full emotional and physiological payload. The dream doesn't just replay the event, it re-traumatizes. Prazosin, by blocking norepinephrine receptors, helps restore that normal low norepinephrine REM environment. It lets the brain do its reprocessing work without the alarm bells going off. Now, the story of prazosin has its own complications. A large multi-site VA trial published in 2018, the PACT trial, failed to show a significant benefit of prazosin over placebo for PTSD nightmares. That was disappointing and confusing, and it led to a lot of debate. Some researchers pointed to methodological issues. The study population was different from Raskind's original cohorts. The dosing protocol was different. The placebo response rate was unusually high. Others argued that maybe prazosin works for some patients but not others, and we need better ways to identify who will respond. The clinical reality is that many individual patients and many clinicians swear by prazosin, but the large-scale evidence is muddier than anyone would like. That's science for you. It's messy. It doesn't always give clean answers. But step back from the specific drug for a moment and think about the broader picture. What the prazosin story tells us, along with the SSRI story, the MAOI story, the sleep deprivation findings, and the IRT research, is that dreams exist at the intersection of neurochemistry, cognition, emotion, and memory in ways that we're only beginning to map. Every intervention that changes one of those variables, whether it's a drug that alters neurotransmitter levels, a cognitive technique that reshapes narrative schemas, or a behavioral intervention like sleep deprivation that disrupts the timing and architecture of sleep stages. Every one of those interventions changes the dream experience, and often in ways that have real clinical consequences. Which brings us to something that's been quietly revolutionizing dream research over the past decade or so. And that's the use of neuroimaging to look at what the brain is actually doing during dreams, not just during REM sleep in general, but during specific dream experiences. Because for a long time, the biggest limitation in dream science was that you could only study dreams after the fact. You'd wake someone up and ask them what they were dreaming about, and you'd get a verbal report that was filtered through waking cognition, subject to forgetting, subject to confabulation, subject to all the biases that come with retrospective self-report. It was like trying to study a thunderstorm by interviewing people the next morning about what the sky looked like. You could learn something, but you were always one step removed from the phenomenon itself. What changed was a combination of better imaging technology and cleverer experimental designs. And one of the most striking studies came from a group in Kyoto, Japan, led by Tomoyasu Horikawa and Yukiyasu Kamitani, published in Science in 2013. What they did was essentially decode dream content from brain activity. They used functional MRI to scan people's brains while they were falling asleep, specifically during the hypnagogic period, that transitional zone between waking and sleep where people often have vivid, fragmented imagery. They'd let subjects drift off inside the scanner, monitor their brain activity, and then wake them up as soon as they detected sleep onset and ask them what they'd been seeing. They did this over and over, hundreds of times per subject, building up a massive database of brain activity patterns paired with reported visual content. Then they trained a machine learning algorithm on the data. They showed it. Here's the brain activity pattern, and here's what the person reported seeing. A person, a building, a car, text, food, whatever. And once the algorithm had learned the associations, they could use it to predict what a sleeping person was dreaming about just from the brain scan before waking them up. And it worked. Not perfectly, not with the resolution of a photograph, but significantly above chance. The algorithm could tell whether someone was dreaming about people versus objects versus landscapes, based solely on the patterns of activity in visual cortex. Think about that for a second. A machine reading the content of dreams from brain activity. It sounds like science fiction, but it was published in one of the most rigorous journals in the world. And what it confirmed, at a neural level, was something that dream researchers had long suspected: that dreaming activates many of the same brain regions in many of the same patterns as actual visual perception. When you dream about a face, the fusiform face area lights up, just as it does when you see a face while awake. When you dream about a place, the parahippocampal place area activates. The brain isn't generating random noise and then slapping a narrative on it after the fact. It's constructing genuine perceptual experiences using the same neural machinery it uses during waking life. And that finding has implications that ripple outward in every direction. It connects to the question of consciousness. What does it mean that the brain can generate a fully immersive perceptual world with no external input? It connects to the question of memory, because the content of dreams is drawn from stored experiences, which means the memory systems are actively engaged during sleep in ways that shape what you see and feel and do in the dream. And it connects to something that researchers are only now beginning to explore seriously, which is the relationship between dreaming and the default mode network. That's the term you'll hear neuroscientists use for a set of brain regions that become most active not when you're focused on a task, but when you're doing the opposite. When you're daydreaming, mind-wandering, letting your thoughts drift without any particular goal. And here's what's fascinating. The regions that make up the default mode network overlap substantially with the regions that are most active during REM sleep dreaming. The medial prefrontal cortex, the posterior cingulate, the angular gyrus, the hippocampus. These areas form a network that seems to be doing something essential whenever the brain turns inward, whether you're awake and staring out a window, or asleep and lost in a dream. This connection started becoming clear in the early 2000s as resting state fMRI studies revealed that the brain is never really idle. Even when you're lying in a scanner doing absolutely nothing, there's a tremendous amount of coordinated neural activity happening, and it follows consistent patterns. Marcus Rachel at Washington University was one of the key figures who identified and named the default mode network around 2001, and initially it was almost treated as a curiosity, background noise, the brain's screensaver, something that happened in the gaps between real cognition. But over time, researchers realized that this network is doing something profoundly important. It's involved in self-referential thinking, in imagining future scenarios, in recalling autobiographical memories, in understanding other people's mental states. It's the network that lets you simulate alternative realities in your head. And when you think about it that way, dreaming starts to look less like some weird biological accident and more like the sleeping version of something the brain does all the time. This is where a researcher named Domhoff enters the picture. William Domhoff, a psychologist at UC Santa Cruz, spent decades studying dream content. He was one of the people who carried Calvin Hall's massive dream database forward into the modern era. And by the 2000s, he was making an argument that would have seemed radical a generation earlier. He proposed that dreaming is essentially the same cognitive process as mind wandering, just happening under different neurochemical conditions. The default mode network, he argued, is the engine of dreaming. When you fall asleep and external input drops away, the network doesn't shut down. It keeps doing exactly what it does during waking mind wandering, generating simulations, scenarios, narratives drawn from memory. The difference is that during sleep, the prefrontal executive regions that normally keep your daydreams loosely tethered to reality are largely offline, so the simulations become more bizarre, more emotionally vivid, more unconstrained. But the fundamental process is the same. And this idea connects beautifully to what Horikawa and Kamatani showed with their dream decoding study. If dreams are using the same perceptual machinery as waking experience and the same network architecture as waking mind wandering, then dreams aren't some alien mode of cognition. They're a variation on something your brain is already doing every time you zone out during a meeting or imagine what you'll have for dinner. The machinery is continuous. The neurochemistry shifts, the sensory gates close, and the simulations become untethered, but it's the same machinery. Now, you might be thinking, okay, that's an interesting theoretical framework, but does it actually help us understand anything practical? And the answer is yes, in ways that are surprisingly direct. Because if dreaming and mind wandering share neural architecture, then disruptions to the default mode network should affect both. And that's exactly what we see in certain neurological and psychiatric conditions. In Alzheimer's disease, for instance, the default mode network is one of the first systems to deteriorate, and patients with Alzheimer's report fewer and less vivid dreams. In depression, the default mode network tends to be hyperactive, stuck in ruminative loops, and people with depression often report more frequent, more emotionally negative dreams. The correlation isn't perfect, and correlation isn't causation, but the pattern is suggestive. dreams may be a window into the health and functioning of this fundamental network. And here's where things get really interesting from a clinical perspective. Remember how we talked about Matt Walker's idea that REM sleep serves as a kind of overnight therapy, stripping the emotional charge from difficult memories? Well, the default mode network framework adds another layer to that. During REM sleep, the hippocampus, which is part of the default mode network, is actively replaying and reorganizing memories, as we discussed with the Maze study. But it's doing so in conversation with the medial prefrontal cortex, which is involved in emotional regulation and self-referential processing. The theory is that this dialogue allows memories to be recontextualized, placed into broader autobiographical narratives, connected to other experiences, gradually shifted from raw emotional recordings into integrated life stories. And the dream is the subjective experience of that process happening. This is speculative, but it's the kind of speculation that's grounded in converging evidence from multiple directions. You've got the neuroimaging data showing which regions are active. You've got the neurochemistry, the low norepinephrine environment that Walker emphasized. You've got the behavioral data from studies showing that sleep helps with emotional regulation. And you've got the clinical observations from conditions like PTSD, where the whole system seems to break down. Each piece alone is suggestive. Together, they start to paint a coherent picture. But let's talk about something that complicates this picture in a productive way, because science is never as neat as we'd like it to be. One of the most provocative findings in recent dream research comes from studies of people who rarely or never dream, or at least who never remember their dreams. For a long time, the assumption was that everyone dreams during REM sleep, and the only variable is whether you remember it upon waking. And that's largely true. If you wake people up during REM, the vast majority will report some kind of dream experience. But there's a small percentage of people, and some studies suggest it might be around 6 to 8% of the population, who almost never recall dreams, even when woken from REM. And then, there are the truly rare cases, people with specific brain lesions who appear to have lost the ability to dream entirely. Mark Solms, a neuropsychologist working in South Africa, studied these cases extensively in the 1990s, and what he found challenged some long-held assumptions. Solms examined patients who had suffered strokes or other brain injuries, and he discovered that the critical region for dream generation wasn't actually the brainstem REM-generating areas that Hobson and McCarley had focused on. Instead, the lesions that eliminated dreaming were typically in the parietal-occipital junction, or in the white matter tracts connecting the prefrontal cortex to the limbic system. Some of these patients still had normal REM sleep. Their eyes moved, their bodies were paralyzed, all the physiological markers of REM were present, but they reported no dreams whatsoever. Conversely, Solms found that lesions to the brainstem REM centers could reduce or eliminate REM sleep, but patients might still report dreamlike experiences during non-REM sleep. This was a genuinely important finding because it suggested that REM sleep and dreaming, while usually occurring together, are actually dissociable. They're generated by different neural systems that normally operate in concert but can be separated by injury. REM is a brainstem phenomenon. It's about the physiological state, the eye movements, the muscle atonia, the characteristic EEG patterns. But dreaming, the subjective experience of being immersed in a vivid, simulated world, that seems to depend more on forebrain structures, particularly the regions involved in spatial cognition, visual imagery, and motivational drive. Solms connected this to the dopaminergic system. He noted that the white matter tracts whose damage eliminated dreaming were part of the mesolimbic and mesocortical dopamine pathways, the same circuits involved in motivation, reward-seeking, and desire. This led him to propose that dreaming is fundamentally driven by the brain's seeking system, a concept borrowed from Jaak Panksepp's affective neuroscience framework. In this view, dreams aren't just the brain processing memories or running threat simulations or doing emotional therapy. They're the brain's motivational system running in an unconstrained mode, generating scenarios organized around wanting, seeking, approaching. And if you think about the phenomenology of dreams, this actually fits pretty well. Dreams are rarely passive. You're usually doing something in a dream, searching for something, trying to get somewhere, pursuing a goal, fleeing a threat. There's a forward momentum to most dreams, a sense of seeking, even when the narrative is bizarre. Now, this doesn't invalidate the other theories we've talked about. Ravansuo's threat simulation, Walker's emotional processing, the memory consolidation work, all of those can coexist with the idea that the dopaminergic seeking system provides the motivational engine that drives dream narratives forward. It's another layer, another piece of the puzzle. And what's beautiful about where dream science stands right now is that we're at a point where these different threads are starting to weave together rather than competing with each other. Think about it this way. You've got a brain that, during REM sleep, is in a unique neurochemical state: high acetylcholine, high dopamine, low norepinephrine, low serotonin. The default mode network is active, generating simulations using the same perceptual machinery it uses during waking life. The hippocampus is replaying and reorganizing recent memories. The emotional processing centers in the amygdala are engaged. The motivational seeking circuits are running. And the prefrontal executive regions that would normally impose logical constraints and reality testing are largely offline. Put all of that together, and what do you get? You get dreams. Vivid, emotionally charged, narratively bizarre, memory-infused, goal-directed, but logically unconstrained experiences that feel absolutely real while they're happening. And this brings us to what might be the deepest question of all, the one that keeps philosophers and neuroscientists up at night, which is ironic given what we're talking about. The question is this: what do dreams tell us about consciousness itself? Because here's the thing. When you're dreaming, you are conscious. You are having experiences. You are seeing things, feeling emotions, making decisions. Or at least, you believe you are. The dream world feels real to you while you're in it. You don't usually question it. You accept the bizarre premises. You engage with the characters. You feel genuine fear or joy or confusion. And yet the entire experience is being generated internally, with no external input whatsoever. Your brain is building a complete world, with visual detail, spatial structure, emotional texture, narrative coherence of a sort, entirely from its own resources. And that raises a question that goes beyond sleep science and into the heart of what it means to be a conscious being. If the brain can generate a fully convincing reality without any input from the outside world, then how much of what you experience during waking life is also a construction? How much of your waking perception is the brain generating a model and then checking it against sensory data versus passively receiving information from the world? And the answer, as neuroscience has increasingly shown, is that waking perception is far more constructive than we intuitively believe. Your brain is always building a model, always predicting, always filling in gaps. Dreaming is what happens when the prediction engine runs without the error correction signal from the senses. It's the same process, just unchecked. The guardrails are off. The prediction engine is freewheeling, generating scene after scene, character after character. And because there's no sensory data streaming in to contradict it, you believe every bit of it. You're standing in your childhood kitchen talking to someone who might be your boss, but also might be your grandmother. And the floor is made of water. And none of that strikes you as odd. Because the part of your brain that would normally flag those inconsistencies, that prefrontal reality checking circuitry, is running on minimal power. The predictions go unchallenged. And this is the insight that ties so many of the threads we've been following all night into a single, elegant idea. It's sometimes called the predictive processing framework, or predictive coding, and it's become one of the most influential ideas in neuroscience and philosophy of mind over the past couple of decades. The basic claim is this: your brain is not a passive receiver. It's not sitting there waiting for the world to send it information and then reacting to that information. Instead, it's constantly generating predictions about what it expects to encounter, what it expects to see, hear, feel, smell, and then comparing those predictions against the actual sensory signals coming in through your eyes and ears and skin. When there's a mismatch, when the prediction doesn't match the signal, the brain updates its model. That mismatch is called a prediction error. And it's really the prediction errors that drive conscious experience, that create the feeling of surprise, of noticing something, of paying attention. When the prediction matches the signal, you barely notice. The world just feels normal, expected, smooth. Think about driving a familiar route. You barely register the scenery because your brain has already predicted every turn, every stoplight, every stretch of road. But put a deer in the middle of the highway, and suddenly your brain lights up, because the prediction didn't account for that. Now, the person most associated with formalizing this idea in its modern neuroscientific form is Carl Friston, a British neuroscientist working at University College London. Friston's work is famously dense. His papers are the kind of thing that other neuroscientists joke about needing a PhD just to read the abstract. But the core intuition is actually quite beautiful and, I think, quite graspable. Friston proposed what he calls the free energy principle, which is a mathematical framework suggesting that all living systems, including brains, are fundamentally in the business of minimizing surprise. Not surprise in the birthday party sense, but in the information theory sense, the difference between what the system predicts and what actually happens. Your brain is constantly trying to reduce that gap, either by updating its internal model to better match reality, or, and this is the fascinating part, by acting on the world to make reality match its predictions. When you reach for a glass of water, your brain has already predicted the weight, the temperature, the texture. If the glass turns out to be empty when you expected it to be full, you feel that jolt of surprise, prediction error, and your model updates. But most of the time, your actions are shaped by your predictions in a way that makes the predictions come true. You move your hand to where you expect the glass to be, and the glass is there, and the loop closes seamlessly. So what does this have to do with dreams? Everything. Because if waking consciousness is the brain running its prediction engine, with sensory error correction keeping things honest, then dreaming is the brain running that same engine without the error correction. The predictions just go. They generate a world, And because there's no contradictory signal coming from the retina or the cochlea or the skin, the brain accepts its own predictions as reality. Every prediction becomes perception. Every expectation becomes experience. And this is why dreams feel real. They feel real because the mechanism that generates them is the exact same mechanism that generates your experience of waking reality. The only difference is the presence or absence of external sensory constraint. Think about what that means for a moment. It means that right now, as you're lying here, whatever you're perceiving, the sound of my voice, the feeling of the pillow under your head, the darkness behind your eyelids, your brain is constructing all of that. It's building a model, a simulation, a best guess about what's out there, and it's using sensory data to refine that model, to keep it honest, to keep it tethered to the actual physical world. But the model is always there. The construction is always happening. You never have raw, unmediated access to reality. You only ever experience your brain's best prediction of reality, corrected and updated moment by moment by the senses. And that's a profound thing to sit with. It means that in a very real sense, you are always dreaming. Waking life is a dream that's constrained by sensory input. Sleep dreaming is the same dream, unconstrained. The philosopher Thomas Metzinger has written beautifully about this. He talks about how consciousness is a kind of virtual reality generated by the brain, and how we are, in a sense, always inside a simulation. It's just that during waking life, the simulation is anchored to something external, and during dreaming, it's not. Metzinger calls this the ego tunnel, the idea that your entire experience of being a self in a world is a model, a construct, and you are always inside that construct, looking out through it, never able to step outside it to see the raw data directly. Now, this might sound unsettling, but here's the thing. It's also incredibly elegant, because it means the brain has solved an engineering problem of staggering complexity. It has built a system that can generate a coherent, stable, immersive model of reality in real time, updating it hundreds of times per second based on noisy, incomplete, ambiguous sensory data. And it does this so seamlessly, so effortlessly, that you never notice it's happening. You just experience the world. You look at a tree, and you see a tree. You don't see the billions of photons hitting your retina, the edge detection happening in your visual cortex, the object recognition algorithms firing, the memory associations being pulled up, the emotional valence being assessed. You just see a tree. The construction is invisible, and dreams are what happen when that same magnificent construction engine runs without its usual constraints. It's the same system, the same architecture, the same fundamental process of world building, just operating in a different mode. And this connects back to something we touched on much earlier in the night, the default mode network, that constellation of brain regions that activates when you're not focused on the external world. Domhoff's argument that dreaming is neurochemically altered mind wandering, because what the default mode network does, fundamentally, is run the prediction engine in a more free-form way. When you're daydreaming, when you're mind wandering, when you're lying in bed thinking about tomorrow or replaying a conversation from last week, you're running the same predictive machinery, just with a looser grip on sensory reality. And during REM sleep, that grip loosens entirely. The acetylcholine is high, driving vivid sensory-like experiences within the model. The norepinephrine and serotonin are low, reducing the logical constraints, the reality checking, the temporal ordering. The dopamine is active in those seeking circuits Panksepp identified, giving the experience its forward momentum, its narrative drive, its feeling of going somewhere, wanting something, pursuing something. And the prefrontal cortex, that seat of executive function and critical thinking, is largely offline, which is why you don't question the bizarre premises. The prediction engine is generating a world, and there's no one left on duty to say, wait, that doesn't make sense. So when you put all of this together, and I know we've covered a lot of ground tonight, winding through history and neuroscience and philosophy, what emerges is something like this. Dreaming is not a malfunction. It's not random noise. It's not the brain taking out the garbage, and it's not a mystical portal to another realm. It's the brain doing what the brain always does, building a model of reality, generating predictions, processing information, consolidating memories, working through emotional challenges, simulating threats, exploring possibilities, but doing all of that in a state where the usual external constraints have been removed and the neurochemical environment has been radically altered. Dreams are the brain's construction of reality, revealed. They show you the scaffolding that's normally hidden behind the finished wall. And maybe that's why dreams have fascinated human beings for as long as we've been human. Not because they contain secret messages from the gods, though I understand why ancient peoples thought so. Not because they're the royal road to the unconscious, though Freud wasn't entirely wrong that dreams reflect our concerns and preoccupations, but because dreams are the one experience that lets us glimpse the machinery of our own minds at work. They're the curtain pulled back, just a little, on the astonishing process by which 1.5 kilograms of biological tissue generates an entire world, an entire life, an entire sense of being someone, somewhere, doing something that matters. And the science is still unfolding. We're still in the relatively early days of understanding all of this. There are researchers right now, tonight, as you're lying here, running sleep studies, analyzing EEG data, training machine learning models to decode dream content from brain scans, testing new theories about why certain brain regions activate in certain patterns during certain sleep stages. The questions are still wide open. Why do we dream about what we dream about? Why do certain themes recur across cultures and across centuries? What exactly is happening at the synaptic level when a memory gets replayed and transformed during sleep? How does the brain decide which experiences to consolidate and which to let fade? Can we learn to influence our dreams in ways that genuinely improve mental health, beyond what imagery rehearsal therapy already achieves? What would it mean if we could reliably communicate with dreamers, build a true dialogue between the waking and dreaming mind? These are real questions that real scientists are working on right now. And the answers, when they come, will tell us something not just about sleep, but about the deepest nature of consciousness itself, about what it means to have an inner life, about what it means to be the kind of creature that can close its eyes and build entire worlds from nothing but memory and prediction and emotion. But those are questions for another night. For now, what matters is this. Your brain is doing something extraordinary right now. It's beginning to let go of the waking world, to loosen its grip on sensory reality, to shift its neurochemistry toward that strange and beautiful state where the prediction engine runs free. The acetylcholine will rise, the norepinephrine will fall, the default mode network will hum along, weaving fragments of your day, your memories, your concerns, your hopes into something that might not make logical sense, but will feel absolutely real while it's happening. And that's okay. That's the system working as designed. Billions of years of evolution have shaped this process. refined it, kept it because it does something valuable, something we're still not entirely sure how to articulate, but something real and important. So let it happen. Let the thoughts drift. Let the images come and go without trying to hold on to them or make sense of them. Your brain knows what it's doing. It's been doing this every night of your life and every night of every human life that came before yours, all the way back to the very first creatures that slept and dreamed in whatever form dreaming took for them. You're part of that long, unbroken lineage of dreamers. And tonight, like every night, your brain will build you a world. It won't be a perfect world. It might be strange. It might be frightening. It might be beautiful. It might be utterly nonsensical. But it will be yours. Generated by your memories, shaped by your emotions, driven by your own particular version of that ancient prediction engine that every human brain shares. And tomorrow, if you remember any of it, you might smile at how real it felt, how vivid the colors were, how strong the emotions, how convincing the narrative, even though none of it was happening in the external world. And maybe, just maybe, you'll carry with you a quiet appreciation for the fact that your brain can do that, can build a complete reality from scratch, can make you believe in it utterly, can give you experiences that feel as meaningful and textured as anything in waking life. That's not a glitch. That's consciousness. That's the most remarkable thing any known structure in the universe has ever learned to do. So close your eyes if they aren't closed already. Let the prediction engine do its work. Let the world your brain builds tonight be whatever it wants to be. You don't need to steer it. You don't need to understand it. You just need to let it carry you, gently, wherever it goes. The science will still be here in the morning. The questions will still be fascinating. The history will still be full of brilliant, stubborn, curious people who spent their lives trying to understand this one strange, universal, deeply human experience. But for now, for tonight, just sleep. Just dream. And know that in doing so, you're participating in one of the oldest and most beautiful mysteries there is.